Okay, so let's see a few examples. We can take a look at few instructions and try to figure out encoding and find the machine code. And also we can look at how direct addressing and indirect addressing works for few instructions. Our intention here is not to teach you every instruction and how they work and to figure out how the encoding for each of them, and so my intention here is really help you to be able to read the data sheet, right? So that's basically this is all about. So programming language, so if you can understand the data sheet and if you know if you learn some basics in this class, so you can pretty much later on when you need it, you can go ahead and read the manual, read the programmer reference manual and the data sheet, and you can figure things out yourself. So that's the intention here. That's what I'm going to try to do, and we will look at few instructions and figure things out, and hopefully that's going to help you to if you need, so help you to figure things out yourself. Our intention here is not to teach you every instruction and how they work and to figure out how the encoding for each of them, and so my intention here is really help you to be able to read the data sheet, right? So that's basically this is all about. So programming language, so if you can understand the data sheet and if you learn some basics in this class, so you can pretty much later on when you need it, you can go ahead and read the manual, read the programmer reference manual and the data sheet, and you can figure things out yourself. So that's the intention here. That's what I'm going to try to do, and we will look at few instructions and figure things out, and hopefully that's going to help you to if you need, so help you to figure things out yourself. Okay, first instruction we have here is add instruction. Again, there are multiple of add instructions, so like 8-9 of them, I don't remember. We can look at from the table. Let's look at this specific add instruction, add a literal to wn. So basically we can add literal to like a basically constant value to certain register. So basically what happens is here is the definition of the instruction. So take 10-bit literal number and add it with content of wn and put it in wn. So that's basically summarizes what this application, what this instruction does. 10-bit literal plus whatever value in the working register, whatever working register you are using, and puts into the same register. That's what this instruction does. So there is a limitation in this instruction. So even though in some instructions you can do 16-bit, right? So if it is working register to working register, so if you are adding two values in both of them in like a W working registers, then you can do like a 16-bit. But here we have a limitation. It says up to 10-bit. Okay, so it can be up to 10-bit binary value. So that's kind of limitation. And also you have byte-wise operation too. So you can do byte operation too here. So if you read here, of course, if you do byte, then it can only goes up to 2 to the 55, because 2 to the 8 is from 0 to like a 256, right? If it is a byte operation, so the values can be from 0 to 255. And if it is a word operation, so well, again, you cannot do 16-bit word here. There's a limitation. It can be only up to 10 bits. So 2 to the 10 is 1023. So I mean 1024. Of course, it's from 0 to 1023. So that's the limitation. And also, like, you know, a VN can be any working register we have from 0 to 15. So that's how we read it. And then it looks like this instruction can affect all these bits. You know, if you, as a result, if you get a negative number, you can have a negative flag, and you can have an overflow. You know, you know, if you can have like a less than 10-bit number, but if you add with the content of WN, if it is bigger than 10-bit number, so then you have overflow. If you get 0, you can get 0, right? When from the addition, you can have a 0 flag, and you can have a carry flag. So all these flags can be affected. And this is the encoding. So we did one example in the class, but not extensive. So as you can see, this is the like a machine code, right? So this is basically what really hardware understand. So here you have a bunch of constants. So we are not gonna change those. And then here are the definition, like what is B and what is K, and I mean there are B, capital B, K, 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 a bunch of Ks, and then D, 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 and D. So what are these? These are defined here, like a little bit description here, right? So B is the select byte or word operation. So if it is a byte operation, if it is a dot B, then B is going to be 1. If there is no dot B, if it is a word operation, as you know, if you don't have anything, that means a word operation, and it's going to be 0. K bits specify the literal operand, right? So K bits here. So as you can see, 2, 4, and 4. So in total, 10-bit literal number. So that's K. Basically, you're gonna put binary value of the literal here, and then you have D bits select the address of the working register. Okay, so well, if it is W0, it's going to be 0000, and if it is W15, it's going to be 11111, because we can represent 15 in binary as 1111. And if you have some like other registers, then you can put the whatever value represents those registers. Okay, so like you can find more information about this stuff if you go to page 96. A little bit distraction here, but let's go to 96. If you want to know more about what each of those means, so you can see, like when you look at other instructions, you will see some other stuff. So this is like your go-to table to figure out what means what. Okay, so again, this is in the reference manual, program reference manual. So as you can see, KKKK, like a 10-bit K is a 10-bit literal, and then what was the one we were looking for? Let's see, I forgot what was it was KKKK. Then let's see, 104. Well, I'll go back, sorry. So we were not doing this one. Yeah, we were well, and the other one was DDDD, right? So let's go to 96 again. So DDDD means well, WD destination register, right? So, and 0000 for W0 and 1111 for W15. Again, if you're looking for, let's say, if you are using W3, then it's going to be whatever value represents 3, right? So then it's going to be 0011 if it is W3. Anyway, so you can figure out any kind of symbols, and you know, this is table called instruction encoding field descriptors. So you can come and look at this table. Oops, it's 103, I guess. So let's go back. Having problem typing here. Okay, so let's figure out the encoding, binary, like a machine code for this instruction, right? So we're using this encoding structure. Okay, so I have my stylus with me. Okay, let's see, hopefully it works. So then here we have 1 0 1 1, so we're gonna have the same thing, 1 0 1 1, and then again these are constant values. I'm just gonna copy, and then we have 0, and then B. Well, B again, I'm doing the I forgot to tell you which operation we are doing. So using, like, we have two examples here. One is this one, and one is this one. This is .b operation, and this is byte operation, and this is word operation. Let's figure this out. Okay. For .b, well, it's a .b. So then maybe I can just. I'm having problem having enough space here. So yeah, so we can see everything here. So we have 0, and then because it's if you are doing this one, then it's a byte operation, so it's going to be, again here it says byte operation. If it is a byte operation, so it's going to be 1, and then k, and so forth, like 10-bit k is well, it's ff, right? So our literal number is ff. Again, 0x prefix means this is a hexadecimal number, okay, and pound sign means it's a literal. So we have a literal hexadecimal ff. Well, how can we represent ff in binary, in 10-bit? Well, so you know, f can be represented in if you do like we can represent each digit in hexadecimal in 4-bit binary, right? So then it's gonna be, you know, for like a 1111 for f, 1111 for f, then to like the most significant 2 digit is gonna be 0, right? So it's gonna be 0. So I'm keeping like group of 4, right? So like these are a group of 4, so I'm just keeping the same structure. So 0 0, and then like for ff it's 1 1 1, and then 1 1 1 1. Okay, so now I put all 10-bit numbers, k 10-bit k, and then destination, again d bits select the address of the working destination. So our working destination is W7. Well, how can, like, again, we have a 4-bit, and like W0 is 0 0 0 0, and W15 is 1 1 1 1 1. So whatever in between, you know, you can find the address easily. So like 7 can be represented in 4-bit as so obviously 0 1 1 1. Okay, so that's it. That's how we find how can we encode the instruction, like assembly instruction, and figure out its machine code equivalent. So that's the equivalent machine code or for the add instruction, the add instruction we are dealing with. So how can you make sure you did it right? So hopefully we did it right, but there's a nice way to figure that out. So let me show that to you. I can put the same instruction here. I'm just gonna put the instruction here. Add what was the value? So literal hexadecimal ff to sorry, we have comma here, and W7. Okay, so I just this was the code we did in the class. So you can look at so I just added this line. So okay, let's see. So how I'm gonna see like the encoding of this instruction. So there is pretty much we can see everything in the good thing about microcontrollers, we can really see everything going on inside the microcontroller. We can view everything, all the memory bits and special function registers and everything, SFRs. So if you go Windows and if you go debugging, or sorry, maybe there are other tools here, you can watch certain variable, but you can go just the program memory. So you can go target memory views and say program memory, and then you will have this window. This window tells you all the instructions that you have in your program. When you compile it, the compiler converts your C code or your assembly code into this basically converts it to opcodes, right? So like machine code. So I'm gonna rerun this code, okay? Basically debug it again. So now let's see, like if I go to the instruction I have, let's see which instruction I was doing. Yeah, I was interested in this one, okay? So I was interested in this instruction. I want to see the opcode or machine code for this instruction. It's B00FF7. Okay, let's see if we got it right. Oh, okay, so let's see. Oh, I forgot .b though. Sorry, my bad. I forgot something was wrong there. So I forgot to put .b. Hopefully you catch that. So I have to put .b here because we are doing .b it's like bytewise operation. So I'm just gonna rerun it. Okay, so what I did wrong is when I typed it, what I did wrong is I put space between add and .b, so you shouldn't have space there. So be careful about that one. So you shouldn't have a space between add and .b. Anyway, so if I go and find the instruction, you can see that it's here. So this is again like your code converted into opcode, like a single, like you have the whole instruction list here, and we were dealing with this one, so we are trying to figure out this one, right? So, and machine code equivalent is this. Okay, so opcode. Of course, this is hexadecimal, right? This is hexadecimal. So let's see what we got. So this is what we got, right? So, and let's convert this to hexadecimal. Again, we know how to convert the value to hexadecimal. So this is 7. So this is F. This is F. That's how we convert binary to hexadecimal, right? So we group by 4 and then we convert each to the hexadecimal equivalent. So this is gonna be 4, and this is gonna be 0, and this is gonna be so this is like 10, 11, right? So 11 is in hexadecimal, it's equal 10 is A and 11 is B. Okay, so as you can see, we have the same value here. So we have the same value. We got it right. Okay, now let's look at how this instruction affects the content of the working register and also content of the status register. So for every instruction, you have all these information, but on top of it you have really useful examples about how that instruction affects like the registers and status registers, working registers, the memory, and so forth. So if you are having hard time understanding the instruction, you can look at these before and after scenarios and figure out understand how that instruction works. So like let's look at this one. Here we have add.b again, but this is what we did above. And again, remember that this is byte operation. Okay, in byte operation, FF, if you are talking about 8-bit number, so then FF is gonna be -1, right? So because if it is an 8-bit number, let me show you here very quick, bear with me. So if you have an 8-bit number, um, 2 to the 8 is gonna be 256. If this is a signed number, signed 8-bit number or a byte, then half of it is gonna be, positive. So from 100, like from 0 to 127, and then the rest of it is gonna be like from -1 to 128. So you can represent both positive and the negative numbers with this. Sorry, 127. And again, remember, how can you find the negative number? Let's negative numbers with using 2's complement. Let's say we have 1, right? So this is 1 in 8-bit number, right? So in 8-bit value, this is 1. How we can find -1? Well, we do 1's complement first. So for 2's complement, we do 1's complement and then add 1. So 1's complement is gonna be like, we just invert every bit, right? So 1 1 1 1 1 1 0, and then you add 1, right? So this one was +1, so -1 is gonna be 1 1 1 1 1 1 1 1. If you add this, it's gonna be 1 1. So F. So FF. So this is gonna be in hexadecimal, of course. So this is a -1. Okay, so just keep that in mind. Okay, so that's basically why it says add -1 to W7, because FF in hexadecimal, if this is a byte, okay, if this is a byte, and then it is, so it's equal to -1. Okay, in the byte mode. Okay, so basically what's happening here is it says, okay, this is what's obviously this is very easy, but so this was, let's say, assuming this was the content of W7 before. Well, what we do with this operation is we add -1 to it, or we add FF to it. So what's gonna be the result? Well, it's gonna be this value. So let's see that. Okay, let's do it here. So we are adding, I mean, we don't have to do this, but just to make sure everybody is really in the same page. 12, so 1 2 0, like a content of this, plus -1, right? So it's gonna be, so if you're adding these two, or basically subtracting, right? So like you know, adding this with -1 means subtracting this one from this value. So you know, you just say negative then plus like that. So subtraction. So then I mean, x plus -1 is equal to x minus 1, right? Same thing. So that's what I'm doing here. So if you subtract, so then you know 0 minus 1, so you need the carry here. So I'm doing in hexadecimal. If you, then it's gonna be 16 here. If you subtract, you borrow 16 from here, right? So and then 16 minus 1 is gonna be 15, which is f. Well, C, so you borrow 1 from here, so it's gonna be B here, and then 2 and 1. So 1, 2, BF, right? So that's what exactly we got here. So assuming this was the content, by adding -1 to it, this is what we get, which is easy to understand. And then here they are assuming status registers initially. Status register initially, all of them was, you know, there was no flag raised before the operation. And after the operation, it seems like something happened, some flags raised. So let's try to understand what this is. Okay, so let's talk about it. Okay, so I think you remember I showed you this before. This is PIC24 programmer's model diagram. So we have working registers here, and we talked about frame, pointer, and stack pointer, but not much. Really, we don't care at this point. And all this stuff, really, we don't care much at this point. But what we care is this 4-bit. Okay, and maybe sometimes this, but even this is we use very rarely. So if you have like after the instruction, like execution of instruction, if you have a carry, you know, if you are adding or something, if you have carry, and then this flag get raised, and this is 0 flag. If the result is 0, then you have a 0 flag. If you add two numbers and you get, like, let's say if you add two 8-bit value, and if you you do byte operation, and if the value you got is more than the result you got is more than 8-bit, then you have overflow, obviously, right? And if you have word operation, then if the result gets, like, you do 16-bit operation, right? If the result is above 16-bit, which can be the case many times, a lot of times, so then you have overflow flag, and then if the result is negative, you have negative flag. Okay, so these are the lower 4-bit of the the status register. And then these are about interrupts and stuff, so we don't really care what's going on here. And maybe we can talk about DC later. It's digit carry or decimal carry. It's kind of carry, but it's a little bit different than the regular carry. So we can talk about that later. Now let's try to understand why we have 0009 here. Okay, so remember I just showed you the status register, right? Status register, and the lower 4-bit was you had a bunch of stuff. Sorry for my drawing. So we had like a bunch of status stuff. We didn't really care most of it, so we only cared these bits. Again, what was the order? I keep forgetting the order, so I'm just gonna go back to that page. So N, O, V, Z, and C. So N, O, V, Z, and C. Actually, you can see the same thing here. Actually, it's in here. DC, N, O, V, Z, and C. Okay, you can, when you run things, and you can see which flags raised and which flags not raised from here on MPLAB-X. And this is the order that you have. Again, usually we don't deal with the DC. DC is about binary coded decimal, and I can explain later. I don't want to take your time here much. Just let's focus on this one. So basically, when we add these two numbers, right? So we added. So why? I mean, like, okay. So let's look at what does that mean. So 0001 means 0001 means basically, I mean 0009 means this, right? 0000 and 1001. Well, I mean, you know, obviously this operation, this instruction does not affect any other flag other than DC. You can see here DC, N, OV, and Z and C, right? So that's why if they were 0 before, they are going to remain 0, and they were 0 before, we know that, right? So it's because we know the status before. But after the instruction, execution of the instruction, seems like negative flag raised and carry flags raised, and overflow and Z was not raised. Okay, so let's try to understand that. Okay, so question is why carry flag raised? I mean, we didn't have carry, like so basically this bit didn't get any carry or something, right? So why we have carry flag raised? Well, because this is a byte operation, right? So this is a byte operation, and what we did, we added. So byte operation only deals with so when you think like that, so this is a byte operation. I mean, you can put the -1. I guess this is like you can do the same thing with FF. So basically, when you add these two, what happens? You have F, and what is C plus F? C plus F is B, and with carry 1. Okay, well, because this is a byte operation, this carry is just gonna be trashed. I mean, it's not gonna go, and like normally if you had a word operation here, this flag was gonna go here, and you were gonna have 3 here, and then then you have 1. But because this is just a byte operation, not a word operation, so the carry is not carried here. Okay, it's just after here you stop, because this is a byte operation, and this is hexadecimal 2 digits, so it equals to 1 byte, right? So it does not go here and affect this this bit, right? But you have flag raised. I mean, you have a carry, but it's not affecting this bit, so you have carry, right? So C plus F is B with the carry 1. Okay, if you have a question about this, please ask me, and I can explain later. I mean, hopefully you guys will understand this one, but if you have a question, I can answer. So that's the carry part. Okay, so how about the negative? I mean, why we have a negative flag raised, right? So this is for that, and this is for that, and this is for this, and this is for this one, right? So why negative flag raised? Well, because BF is remember I said from like 0 to 127, like with 8-bit, you can represent like numbers from 127 and negative numbers from -1 to -128. So this was your range, and BF is in that case is negative value, right? So BF is negative value, and you can figure out its negative value in many different ways. Let me show you with the calculator without wasting much time here. Why this is happening? Okay, calculator. Okay, I have my calculator here. So what I'm gonna do, like, you know, so you can represent from 0 to 127 in decimal, of course. So I'll just put decimal. So decimal 127 is in hexadecimal equals 7F. Anything bigger than this is gonna be a negative number, right? So you know, 7F is gonna be like one digit bigger than this is gonna be what? Can you tell what's like if we like a 7F in hexadecimal? If you go one further, what's gonna be the value? Okay, what's the in hexadecimal number bigger than 7F, which, I mean, again, in decimal 127. That's the maximum positive number we can maximum value, the positive value we can represent in hexadecimal. So one bigger than that in hex is gonna be, if you add 1 to 7F, it's gonna be 80, right? So it's gonna be 80. But 80 is not. Okay, let's figure out what 80 is equivalent. You know, I mean, anything above 7F is going to be negative value. Now we are trying to figure out what negative value it represents, right? So 80 in decimal is going to be equal to, I mean, in binary is going to be equal to 0, 0, 0, 0, right? So let's find 2's complement of this value. So this is 80. First we do 1's complement. So 0, 1, 1, 1, 1, 1, 1, 1. So we invert every bit, and then we add 1, right? So this is 1's complement. 1's complement, and then here we add 1 and it becomes 2's complement. So then if we add so now if we add these two numbers, like then 1 plus 1 is 0, so then we have a carry, right? So like carry of 1, so 1 1 is 0 again, and then we have carry, so 0. And if you keep going, like if you have carry and then you go, so, and then you have, if you do whole thing, you get this. What is that? What is this value equal to in decimal? This is 128. But again, it represents, this represents negative 128. Okay. And again, in hexadecimal, if it's a byte, 80 represents negative 128. So that's why we have a negative flag raised. Okay, so that's why we have negative flag raised here. Hopefully you understand. We started with the difficult one, maybe in that sense, but hopefully you understand what's going on. And I tried to explain every detail. I hope I didn't make it too long and boring, but I'm not sure sometimes where I should stop and how much detail, how much background I should cover. Hopefully this helps. So then for this one, if this is an add operation, if this is an, I mean, so if this is the same operation, but if it is a word operation, ff is not -1. If it is a word, as a word, like, you know, if it's a word, ff means, if you are talking about a word, not a byte operation, ff means, like, ff, when we say ff, like, even though you might not see zeros there, but you have like 2 zeros here, like, you know, basically in like 16-bit, as a 16-bit value, this is how we represent you know, ff in hexadecimal, right? So again, this is hexadecimal value, and if you don't put these zeros, like, you know, basically the like compiler will assume, well, you have zeros there, you know, these zeros does not affect the value, but it kind of tells you it's a 16-bit word, right? Yeah, so in that case, this is not a negative value or something, and it's just ff, and you put this value into w1. Okay, so here's what happens. Well, you are adding same content, like you w1 have the same content, and you add you know, now you add ff on top of it. Ff on top of it. Let me open another page. So in this case, what happens, because this is a word operation, so you have 12z0, and then you add ff. Well, so what happens? So you have f here. C plus f is b with carry 1. Now this carry, you know, goes to this digit, right? So then you have 3, 2 plus 1, 3, and then you have 1. So the content of this register is now 13bf. See, here the carry didn't move beyond this first 8-bit or byte, but here it was able to move beyond this first 8-bit and or byte. So because this is a word operation. Okay, so how about the status registers? As you can see, in this case, we don't have any flag raised, right? So none of them raised because, well, as a result of this, the whole thing, whole addition, we don't have any carry, right? So we don't have carry that did not use or something. So it's just so that's why we don't have any carry. And then this number in as a word is not a negative value. Okay, so that's why we don't have any flag raised for negative. Hopefully this helps. And then, you know, that this is kind of, I mean, again, I'm not trying to teach you this operation. I'm just trying to help you understand this, how we read the manual, and just try to make sense of it. So you can do same thing for pretty much any other. You can read the other instructions a similar fashion, but some other instructions might have some other like the, you know, addressing modes, so it might make them a little bit complicated. So I will do one more example, and then that will be it. Okay, let's do another example. This time I'm doing the instruction, another add instruction, but it's in page 104. Okay, this is kind of similar instruction, like it's another add operation, but this has different kind of operands, right? So it has WB base like a working base register, and then you have 5-bit literal this time, so it can only handle 5-bit literal, and then you have destination register here. So it has 3 operands, right? And well, it seems like this one can do like indirect operations too, right? Indirect addressing modes too, sorry. And the previous one couldn't do any indirect addressing. Okay, it could do only direct addressing, and this instruction seems like can do a bunch of other indirect addressing modes, can work with different addressing modes. In terms of you know, of course, if it is a 5-bit literal, the values can go from 0 to 31, obviously. And then destination and base working registers can be any of those registers in between, and it can affect these status registers, and this is the encoding. Okay, so first thing we want to do is figure out the opcode or encode, like or machine code for this instruction. I mean, well, of course, this line. Okay, let's say we run this line with our microcontroller in our microcontroller and figure out what should be the opcode for this instruction. Okay, so again, we are doing example 2. I'm just skipping example 1 this time. Okay, so we look at here. So I'm just gonna have a Word document here to be able to write. Again, it's a 24-bit encoding, right? So like you have this constant values that you cannot change. So I have 0, 1, 0, 0, and then I have another 0 here, and then I have www. Again, what is that? W bits select the address of the base register. Okay, so address of the base register. Again, I already did this, but if you want to know what is again www more, you can go page 96, and here it says www is a base register, select address is 000 for W0 and 1111 for W15. So if you have another register, so the address is going to be according to the whatever register you are using. So so let's go back 104. Okay, so here, so then what's my register? Base register is W0. So, well, www is gonna be, oh sorry, I'm doing the wrong one, sorry. My base register is W3, so that's why W3 in 4-bit, so it's gonna be 0, 0, 1, 1, right? So 0, 0, 1, 1. So 0, 0, 1, 1. And then B is gonna be 0 because this is a word operation, right? So capital B, it says here. So the explanation is here, here. So B is gonna be 0. And then Q, Q, Q. What is Q, Q, Q? Q bits select the destination addressing mode. Okay, so this is important. It's not talking about the address, it says addressing mode. So we have to look at what is QQ Q means. Let's go back to that table. So when you go here, QQQ addressing mode for WD destination register. Well, that doesn't tell much. We had this same line in the instruction page, but let's go look at this table. This table really tells you what should you put for QQQ, and as you can see, for different addressing modes, you have different QQQ values. In our case, we had pre-decrement, indirect with pre-decrement. So this was our format, if you remember the instruction. So that's why it's gonna be 0, 1, 0, 0. Keep this in your mind. So the QQQ value for this is going to be 1, 0, 0. So let's go back to the page. So see, it's pre-decrement indirect, right? Indirect with pre-decrement. So that's why QQQ is going to be 1, 0, 0, 0. Sorry, 1, 0, 0. So then Q is going to be 1, 0, and then this Q is going to be 0. So the DDDD is what? The bit select the destination register. So now, I mean, like the same thing with the www. This is for base, and and DDDD is for the destination. So which register we use? W4, right? So W4 is gonna be then let me have this here. W4 is gonna be then 0 1 0 0, right? So this is Q here, so 0 1 0 0, D D D D. So we took care of that. And then you have 1 1, so that's basically constant, so you're just gonna put 1 1 there. And then we have K K K K K, so like 5-bit K. What is that? K bits provide the literal operand, a 5-bit integer number, right? So, well, what's our literal here? It's 6, right? So 6 in hexadecimal is equal to 6 in decimal, same thing, right? And then how can I represent this in binary? Well, it's gonna be, so it's gonna be 0 0 1 1 0, right? So this is 5-bit literal, 5-bit. So, and content of it, like basically it was 6 as a value, it was 6. So this is how I express 6 in binary, 5-bit binary. Okay, that's basically it. So we got the whole thing. So I mean, of course, this is in binary. It doesn't look pretty, but we can convert it to the hexadecimal value. So if we group them by 4, so this is gonna be 4 1. This is what? This is A, because 8 plus 2, A, 10, which is equal to A in hexadecimal. So this is 2, this is 6, and this is another 6. So in hexadecimal, it's 4 1 A 2 6 6. Well, is this correct? Did we did it right? So let's check it with MPLABX. So what I did is, by the way, I was recording the same thing and I didn't hit the record, so I was just I'm just repeating same thing again. It took me, I guess, another 10 minutes. I hate recording lectures, pre-recorded lectures. So what I do is I copy from here. You know, I just copied from here and paste it here. So this is, I am not going to do it again. So this is the instruction that I was examining, right? So, well, what's happening here is, what I'm going to do is I'm going to run this. So when I run this, compiler will convert this, my code, my assembly code, into the, you know, opcode and or machine code. And so it's, let's see if it is going to be successful. Yeah, it was successful. So this is the instruction I'm looking for, right? So add, but this was the example I was doing, which is this line. So here you can see opcode is 41A266, which is the exact same thing we got, right? It's 41A266. So we were able to find the right opcode. Okay. So this is correct. Okay, so that's the opcode part, and let's see also what's happening internally. You know, what's happening in the working registers, in the memory, and stuff like that. How this indirect address, pre-decrement indirect addressing works. Okay, so this is before the instruction executed, right? So we have W3 and W4, and then we have these memory locations, and let's see what's happening. Okay, let's look at this one now. So here we have add W3 with the literal 6 and put it in here, right? So again, explanation here, same thing, add W3 and 6 word mode, right? And store the result in this indirect addressing pre-decrement W4. Okay, so this is before and this is after. Okay, so again, remember in this case this is indirect addressing. So what's in, like, basically this W4 holds the address for the location, right? So this is so like let's add W3 and 6, right? So W3 and 6. So if you add, let me have it here. So W3 is 6006, and the 6, and then we add 6, literal 6. So if we add these two, 6 plus 6 in hexadecimal, I'm adding in hexadecimal 6 plus 6 is 12, and which makes in hexadecimal C, so 006. So that's in hexadecimal, right? So, well, is this instruction is going to change the content of W3? No, it's just we just need the content of we need the content of W3, and then the literal is not going to change anything. So like W3, like this is the initial condition before executing the instruction, and this is the after. So obviously W3 is not changing. Okay, and so how about W4? Well, here it says basically it says this is pre decrement, right? So first you decrement the value. So basically W4, instead of being 1000, it's gonna be 0FFF, right? Why? Because if this is a word, if you decrement by, like, if you decrement the instruction, so like current address value in W4 is 1000, and if you gotta decrement, like, because this is a word operation, so you decrement by 2, so then this is gonna be E F F. Again, I'm doing in hexadecimal, so you can do it yourself, and or you use calculator, you will see that that's what you get in hexadecimal. These are 2 hexadecimal numbers. So that's why W4 content is changing from 1000 to 0FFFE, because 1000 minus 2 is FFFE. Okay, so how about anything else? Well, where the sum goes? Sum goes into that address, right? So like basically you first decrement the the content of the W4, and well, again, this W4 holds the address location, so you decrement that and you get FFFE, and then basically this instruction goes to that address. Instead of going the address 1000, it's not going here. So if you didn't have any decrement here, it was gonna go to address location 1000. But because you have pre-decrement, first it decrements the address location, so you get FFFE, so it goes that address and puts the sum in there. Okay, so puts the sum in there. So data location 1000 content did not change, it's same. But again, what changed is FFE, right? Because first, again, this indirect operator instruction says first decrement the address location in W4 and put the sum value in there. Okay, in that decremented address location. So current address location is 1000. You decremented it by 2 because it's a 2 byte, so one word 2 bytes, so you have to keep the alignment right, so you have to decrement by 2. So 1000 minus 2 is FFE, and it goes that address location and puts the sum there, and that's it. So what changed? content of W4 changed because we decremented it, and content of FFE changed because that's where sum we put the sum, and nothing else changed because, I mean, status register didn't change because we didn't do, I mean, there's no negative value, there is no you know, the carry or anything like that, so status register did not change in this case. Hopefully this helps. Again, I'm not trying to teach you like instructions one by one. So I gave you two instructions, like two different type of add instructions, and we did you know, the figure out opcode for or machine code for those, and we tried to look at these examples and figure out what's happening. So hopefully you, like, based on what you learned from here, you can look at other instructions and you can figure out yourself what should be the opcode, or what should, how the content of the registers and the memory locations and things like that gonna change based on these examples. Again, for every instruction you have these examples, very helpful. So you use the tables I referenced, and you can use all other information to find whatever necessary to understand the reference manual and data sheet. Again, the ultimate goal is to being able to understand these documents. Okay, it's not gonna happen overnight, but we'll slowly we will get there. Okay, I would like to mention about one more thing about special function. I mean, status registers. Again, when I said when you can see status registers and their status bits and their status here. You know, carry bit, 0 bit, overflow, and negative, and digit carry or decimal carry. Status bits. So if, as you go through the, like, you know, you step into each instruction, depending on like the if it is a capital letter, that means you know, you have a if a C is capital, that means you have a C flag, and if it is Z capital, you have a Z flag. If they are lowercase, and then you don't have those flags not raised. This is one way of seeing the, you know, the status register. The better way, maybe, you know, like the other way is you know, you can go to your, again, the memory views here, target memory views, and you can go to same place like a program memory. Here you have SFRs, special function registers. If you click that, you will have another tab here. This will have all the registers, all the special function registers, you know, other than, like, you know, like a regular memory stuff. Everything is gonna be here, including, you know, working registers, you know, and everything is gonna be here. Special registers is also gonna be here, and you can see from here that special registers like a 16-bit, and again, remember, we don't really care anything, like we really care at this point the first 4 bits, because those are carry and 0 and overflow and negative flags. So you can see their status. If it is 1, the flag raised, and if it is not, flag not raised. So obviously you can see the same thing here. So 1 being flag raised, and here it's a capital, that means it's flag raised, and another one for 0 flag, it's raised, and it's capital here, that means it's raised too. So this is another place that you can, you know, observe and monitor the status registers. Of course, from here you can observe anything else you want, you know, like a port A and port B and lat A, lat B, and, you know, trees A, trees B, like everything, or timer registers and everything, all the registers are listed here, right? So you can observe like all special function registers from here. So that might come handy as you do as you run your program, as you debug and see really what's going on internally. So this might be something you want to use. And that's it for this video. I'm not gonna add any other parts. Sorry for taking this very long.